Hello, and today I'll be describing 3 uses of the moment-generating function. If you don't already know what this is, I'd recommend going out and learning about it so you can get something out of this video. Alright, so the first use is, let's say mx of t is the moment-generating function for some random variable x. Then the nth derivative of mx of t evaluated at 0 is equivalent to the expected value of x to the n, otherwise known as the nth moment of x. And this is useful because sometimes finding the nth moment directly through the density function or the mass function, that can be quite difficult. So this just provides another avenue to find the nth moment of a random variable. Alright, so the second use is a little bit less general, but let's just say x is normally distributed with mean mu and variance sigma squared. And let's set y equal to e to the x, making it log normally distributed with parameters mu and sigma squared. Then note that mx of t, defined as the expected value of e to the tx, is also equivalent to the expected value of y to the t. So if we want the nth moment of y, we can just simply evaluate the moment-generating function of x at n, which would be e to the mu n plus sigma squared n squared over 2. That's very convenient because we don't actually have to take the derivatives to find the nth moment of this log normal mu sigma squared random variable. Now the last example is the Chernoff bound, where let's say x is some random variable, and we're curious of the probability that x exceeds or equals some value a, and we can bound it above by e to the negative ta times the moment generating function of x evaluated at t, and we just need mx of t defined, and t needs to be greater than 0 for this inequality to be derived. And let me just go through a quick example of this Chernoff bound, because it's not really immediately obviously useful. So let's just stick with the normal situation here. So let's just say x is a standard normal random variable, and we're curious of the probability that x exceeds 5. I mean, if you know the standard normal distribution is going to be very low, but let's just bound it above and go through these motions really quickly. So it's bounded above by e to the negative 5t times e to the t squared over 2. That's just this with 0 evaluated for at mu and 1 for sigma squared. Alright, so simplifying this down, we get e to the t squared over 2 minus 5t. And this attains a minimum, you can trust me on this, at t equals 5, giving e to the 25 over 2 minus 25, which is e to the negative 12.5, which is essentially 0. It's an incredibly small number. So we can bound this probability above by a very small number, and we can know it's basically not going to happen, even though we didn't find the exact probability. So that's just another usage where you don't actually have to differentiate the moment generating function for it to be useful. Now I hope you enjoyed this video, and thank you for watching.